Okay, so we've been using all of this logic to build towards something that we're going to be doing in geometry, which is writing proofs. And essentially what a proof is a building a logical case step by step from information that you're given to the conclusion that in a lot of cases you're being asked to prove. So one of the things that we need to do is we need to discuss certain of these properties that we have in mathematics that we are going to apply step by step. So here's a list of properties of equality. And a lot of these will make a lot of sense to you because you already know them intuitively. Okay? The addition property. If A equals B, then adding the same amount C to both sides, A plus C equals B plus C. Okay? If it starts balanced and then you do the same thing to both sides, it stays balanced, okay? And if you had me in algebra, this is well covered ground. Same thing with subtraction property, multiplication property, and division property, right? You subtract the same amount from both sides, it stays equal if it started equal. Same thing with multiplication, same thing with division. Now this little note here, C cannot equal 0, addresses the rule in mathematics that you cannot divide by 0. It's undefined, and what that means is you get results that are just funny. The mathematics doesn't work out because it's not something that you're legally allowed to do. Okay? Those are the four that you make sense of. Now these are a few that you intuitively understand, but you need to be able to use their names. The reflexive property, A equals A. And you can think about the reflection in the mirror. Let's say the mirror is running along the equal sign, and what you're seeing is the same on both sides. Okay, it's reflecting back over itself. Reflexive property. Okay, not to be confused with the symmetric property, which is very similar, but the symmetric property says that if A equals B, then you could switch the sides of them and B equals A. Now, it's not reflexive because if you look at this right here and you put the mirror along the equals line, you're not getting the same thing on both sides like you are when you reflect it across equals. Okay, so that maybe is a way you can remember it. But you can switch the position of them and it's symmetrical. And this is an interesting one that's going to come up a lot, the transitive property. If A equals B and B equals C, then A equals C. And I always use the example, if I'm as tall as Jack and Jack is as tall as Jenny, then I'm as tall as Jenny, okay, by the transitive property. And the last one here in this list is the substitution property, that if A and B are equal amounts, then B can replace A in any expression because you're not changing the amount that you have there. Okay? Those should intuitively make sense. You're going to want to have this list and refer to them. One last idea that we're going to be talking about here and referring to is the distributive property, which says that if you're multiplying the sum B plus C, in parentheses, by A, each thing gets multiplied by A. And you already know that. And it's the same thing with subtraction. If it was B minus C, each thing would get multiplied by A, so you would get A, B minus AC. Okay? All rules that you should hopefully be able to easily make sense of. And we'll apply them step by step to build a case from what we know to what we're trying to find out. This here is a little note that just kind of describes why they referred to the distributive property in particular right before this problem. And here's essentially the case. If you have 2x plus x, then you have coefficients of 2 and 1. This is an invisible 1, coefficient of 1. And so you could really say, okay, I'm going to factor out that x for a minute and say that's just 2 plus 1 all times x, which is equal to 3x. You'll see that in a second. But that indicates an important thing that may come up, which is that you might have to factor something out from both parts. Okay, so here's the problem. Justify the steps when solving the equation. What is the value of x? And this is what we've got over here. Okay, justify each step. Well, what do we know about this? These two angles, angle AOM and angle MOC, are a linear pair. Okay, so what can we do with that information? They're supplementary because angles that form a linear pair are supplementary. Okay, that's actually a justification here, saying we're making a statement here of what we know based on the illustration or the diagram. Okay, and that's how we justify saying that they're supplementary. From there, we can then write that, note that they're talking about the angles here, Here we're talking about the measures of the angles. The measure of angle AOM and the measure of angle MOC, when added, should equal or will equal 180. That's the definition of supplementary angles. Again, what you're doing here is you're justifying this statement that you made with this justification or reason. Okay, so then what we do, remember, if you know something is equal to something else, you can substitute it in. If A and B are equal, then wherever A is, we can put B in its place. So that's what they're doing here. They're saying measure of angle AOM, well, we know what that is as an algebraic expression, so we can substitute that in. And same thing here with the measure of angle MOC. We know what that equals as an algebraic expression, so we can substitute that in. Okay, and we do that with both of them. Now what can we do? Distributive property is essentially, it's a funny way of saying it. I would describe this as combining like terms, and that's what I would encourage you to write instead of distributive property, is just combine like terms, 2x and x. Okay, and if you wrote combining like terms, that's fine. Now, subtraction property of equality, it doesn't show it, but you subtracted 30 from both sides. And guess what we're going to do next? We will do the division property of equality, divide both sides by 3. You're not showing the math that you're doing, but you are showing the result, and that's fine. So then that's what you've done there. You've proven this statement here. What is the value of x? You've justified your explanation how to get from what you know all the way down to what the value of x is. Okay, so try this with the Gauda problem. See how you do. And I just wanted to add a little note here just to be clear. This is definition of an angle bisector, which should have helped you. So you should know what that was referring to, okay? And addition property of equality, subtraction property of equality. This is another line below it, distributive property. So those are the 4 steps. Now, as this says, some properties of equality have corresponding properties of congruence. If we have properties of equality, like the reflexive property of equality, we can say the same thing for figures that are congruent. Segment AB is congruent to segment AB. Angle A is congruent to angle A. And this seems like, well, yeah, of course, but you'll see that we'll want to refer to that in the course of building our case, okay? Symmetric property, if segment AB is congruent to segment CD, then symmetrically we can switch their position and that's still true. Same thing for angles as segments, okay? And transitive property, if this segment is congruent to this segment and this segment is congruent to this segment, then this first segment is congruent to that segment. Yep. And it works the same for angles. And notice here what they say. If angle A is congruent to angle B and angle B is congruent to angle C, then angle A is congruent to angle C. But these could be switched, and it's still true that since they're both congruent to angle B, they're congruent to each other. So even if you're given them out of order, you should still be able to see what 2 things are both equal to B and therefore are equal to each other. Okay? All right. Now we're going to say what property are we using here? And they give us these statements. What did we do here? What's the name of the property of equality or congruence that justifies going from the first statement to the second statement? Okay. Well, what did we do here? We subtracted 9 from both sides. So that's going to be the subtraction property of equality. Oops. And how do we know that it's the subtraction property of equality? Well, how do we know the difference between equality and congruence? Okay, numbers are equal, so those would be properties of equality. But figures and corresponding parts, we say, are congruent. So well, it's telling us what the next one is. Let's take a look at it. What do we got here? Angle O is congruent to angle W, and angle W is congruent to angle L. So therefore, angle O is congruent to angle L. That's transitive property. Okay, and when you think of transit, you think to move from one place to the other. And what we're doing is we're moving from here to here through this. Okay, we're saying if this is equal to this and this is equal to this, then that is true. And obviously, this is an obvious property of congruence because you can see the symbology for congruence versus here. the symbology for equality. And of course, you should know what this is. They're not talking about the angles themselves, they're talking about their measures, and their measures are equal, and that's why you see equality here. Okay, well, what's going on there? Well, we're switching the position of the two, right? Remember what that looks like? That is, oops. Thanks for your patience. That's the symmetric property. Remember what I said, if you want to know the difference between reflexive and symmetric, you can imagine drawing a line down the equals line. Is it a reflection of itself? Is it actually itself? That would be reflexive. Okay. Symmetric is just like it looks the same in both directions. Hopefully that helps you. Now, what you got a problem? Let's check it out. Okay, now this is what it's all been leading up to. This is a proof. If you had me in Algebra 1 last year, you'll remember that a proof is plugging the number back in and checking to see whether that gives you a true statement, okay? This is a different type of proof. This is a geometric proof where you're using deductive reasoning to build your case from what you know to what you're trying to prove, okay? And a proof logically shows why a conjecture is true. So you are using these properties that are always true, and therefore you know that the case that you build is true when you get to the bottom because it's always true if you're able to apply it. Now, a two-column proof looks like this. You have a statement like the measure of angle 1 is equal to the measure of angle 3, and then you have a reason why you know that. In this particular case, and this is going to happen a lot, is that you're given some piece of information. So you'll need to state it, and you'll say, that information was given to me, right? Just write given. And then you'll make other statements, and you'll tell why you know what you know, okay? And it says each statement must follow logically from the steps before it. You can't say something that you didn't establish as a truth first, okay? And you'll get examples of that. But the diagram below shows the setup for it, and this is what you're going to do. And notice what the last line here is. They want you to prove this. So as you make your list of statements, here to here to here to here to here, the very last statement that you're going to make is what you're trying to prove. And you're saying, now I can say this, this is why. And it's the final reason of all of those steps. Okay? So you're going to be doing this. Let's take a look. All right, so let's do it. Let's write this two-column proof. Given that the measure of angle 1 is equal to the measure of angle 3, and we are given that partly in the diagram by seeing these angle marks, you're going to prove that the measure of angle AEC, this right here, comprising angle 1 and angle 2, is equal to the measure of angle DEB, which comprises angles 2 and 3 together, right? Okay, so this is what we know, this is what we're trying to prove. And let's make this as our plan. We're going to add the measure of angle 2 to both of them. If we had this and this are equal, then adding the same amount to both of them in the form of the measure of angle 2 should do it, okay? So that's going to be the plan. How do we do it? We say what we know. Statement 1, measure of angle 1 is equal to the measure of angle 3. That was already given to us here, okay? Now, measure of angle 2 is equal to the measure of angle 2. That's the reflexive property of equality. And why would we want to do that? Well, we want to be able to state that we are adding the same amount to both sides when we go to this next line. The addition property of equality allows us to say the measure of angle 1 plus the measure of angle 2 is equal to the measure of angle 3 plus the measure of angle 2. So by saying we know that this is equal to itself because of the reflexive property of equality, we're allowed to add that equal amount to both sides. Okay? Once we do that, we now can say this. The angle addition postulate allows us to, notice they have two lines here. We're going to make these two statements together. We're saying the measure of angle 1 plus the measure of angle 2 is equal to the measure of angle AEC. Remember, we have this angle addition postulate from the very beginning that says you can add two angles together that share a common side, and that will give you the measure of the larger angle that they make. And you're going to do that for angles 1 and 2 here for angle AEC, and you're going to do it here for angle 3 and 2 for the measure of angle DEB. Okay? And since we have this statement here in line 3 that the measure of angle 1 plus the measure of angle 2 is equal to the measure of angle 3 plus the measure of angle 2, then what we can do is in this right here, where we have these two together, we know that from step 4, this is what's equal to this plus this. So we're going to substitute for this, we're going to put in this. And there you see it there. Okay. And for this, the measure of angle 3 plus the measure of angle 2, we know that that's equal to this measure of angle DEB, so we substitute it in here with what it's equal to here. And look at what we've done. We've proven what we wanted to prove. Okay? That's worth taking a look at a second time, but we made a good case for it. And that's always your last line, as it says. Okay? So your got it problem is to write a two-column proof on this. If you know that segment AB is congruent to segment CD, and you do, then you're going to prove that segment AC is congruent to segment BD. And if you see where we're going here, you will be applying this kind of thinking that we used for angles for these segments. Okay? Give that a shot and truly write it out, because this is a skill that you're going to need, and it's the very last thing we're doing in this lesson. So write that out step by step, see if it matches what we have as our answers. Now, one thing you'll notice here is that they did not write this as a two-column proof. That the answer book is really giving it to the teacher for the teacher's reference. Okay, so when you have this, it's not set up like this, although you can see here that it says the statement and the justification or reason. Statement, justification. Statement, justification, or reason. Statement, reason. Statement, and there's two statements there, as you can see, that separated by the comma, reason. Okay, so read it like that. See how you can make sense of that. All right, this might be a good one to do the lesson check problems on. So why don't you write these down, compare your answers when you have answers for everyone that you are able to answer, and particularly make note of the ones that you weren't able to put an answer down for, because that means that that's an area that you're still looking for understanding from. Okay? Good luck with this.